All right, so today we're going to talk about colligative properties. Colligative properties refer to how the properties of your solution change as you add solute, which could be your salt, sugar, etc., whatever you're dissolving into your solvent, or remove solvent. So essentially you are increasing the saturation of your solution. All right, and so that's going to affect your solution in 4 different ways. The first one is vapor pressure lowering. So that attraction between particles of your solute and solvent, therefore those bonds and that attraction keeps those molecules from escaping into the vapor state. So from changing from liquid to gas. So adding solute is going to lower that vapor pressure. So what you see here on the left is your pure substance. So you've just got water in the beaker, and as you can see, there's nothing blocking these water particles from being able to escape into a gas. So as they gain energy and they escape your container from water and turn into a gas, they then create vapor pressure. All right, so the particles escaping into a gas creates an increase in vapor pressure, but what happens is as we dissolve a solute into the substance, look how much space is made up of your solute particles, right? So those solute particles take up some space in between, and therefore less of your water particles are exposed to the surface so that they can escape. All right, so therefore that lowers that vapor pressure by basically trapping those water particles in, and the attraction between particles holds them in tighter. All right, so here your water and your solute is attracted together, and it's going to have a little bit more of a hold on these, in addition to taking up the space so that your particles can't easily escape into vapor. All right, the second property that's going to change as we increase the saturation of our solutions is the elevation of a boiling point. So the vapor pressure determines the boiling point. As we lower vapor pressure, our boiling point is higher. So think about if you are boiling a pot of water on the stove, and as it boils, vapor comes off of that pot of water, right? So the more it boils, the more the vapor pressure comes off. So if the boiling point increases, therefore it takes a lot longer for your water to start to boil, creating less vapor pressure. So the boiling point of a solution is higher than that of the pure solvent. So when you're cooking on the stove and you add salt to the pot of boiling water, all right, that salt, what it actually does is increases the boiling point of the water so that the water is able to get hotter before it starts to turn into a gas. Typically, it may start to boil at 100 degrees Celsius, as we know about water. If it's pure water, 100 degrees Celsius, it's going to start to boil. But if you add a whole bunch of salt to it, your water may start to boil at maybe 102, 103 degrees Celsius as you add solute to your water. So why this happens is, again, similar thing with the vapor pressure, as it heats up, look at all these particles that are just free to escape into the gaseous state, right? They're able to escape, build up some vapor pressure. But what happens is once we dissolve our solute into your solvent and create a solution, now there's an attraction between these particles, and your water particles can't escape as easily. Look, it bumps into the solute and gets bounced right back into the container. So basically all these little solute particles are trapping in the water particles and keeping them from evaporating and escaping into a gas. If they can't escape into a gas, then they can't evaporate. So eventually, as the temperature gets higher and higher and higher as it goes along, then the energy that they gain is so much that then these water particles are able to just push on past and escape out of the container. So your colligative properties, the third property that increasing the solubility is going to change is a freezing point depression. So what does this mean? It means that it's going to lower the freezing point of your substance. So that solute breaks up the pattern, that little lattice that your solution makes when it freezes, and therefore gets in the way, making the freezing point lower. You would see this when you think about why do they put salt on the roads in the winter, right? So that salt then mixes with the water that's falling, frozen water, that's ice, right? As it falls as snow, it mixes with that and prevents the roads from freezing. Why? It lowers the freezing point. So instead of the roads freezing at 32 degrees Fahrenheit, it may freeze at 31, 30, a little bit lower. So it's got to get a lot colder outside before it's going to freeze. Mostly we talk about Celsius, so instead of it freezing at 0 degrees Celsius, it may start to freeze at -1, -2, and so forth. It's got to get a lot colder before that water is going to turn into an ice. So again, why does this happen? Why does the boiling point and the freezing point lower down? Well, as you can see, when your water freezes, it wants to make this nice, pretty structure all lined up to where all your particles stick together nicely and form a little lattice. But if we have a solute mixed in, these particles aren't able to make that lattice as well. They aren't able to make that clear structure of a solid and get tightly packed in. So with this in the way, it requires a lot more particles to get combined together in order for that lattice to be formed and for the solid to be created. All right, and then as you begin to boil things, remember, there's particles in the way so that they can't escape. So freezing point lowers, boiling point higher. So think of, why do you put salt on the road in the winter? And why might you put salt into a pot of boiling water? So we can figure out how much it changes our temperature using this formula right here. All right, so our delta T is the change in temperature. So final minus initial. I is the number of particles. If you have a covalent compound, you always have only one particle, equals always 1. Now, if you have a ionic compound, it would either be, most of the time, 2. All right, so you have, for instance, NaCl. There's your salt. We know that that is a +1 and a -1. So those right there are 2 separate particles. So your I in this case would be 2. All right, again, all covalent compounds will be 1. They're only one molecule, one particle all stuck together. NaCl is 2 different particles. Here's 1, here's 2. 2 separate particles coming together through an attraction. All right, so we'll look at some examples of how to determine the number of particles. And then K is your molar constant. Constant means it always remains the same. We will always use the same number depending on which equation we're dealing with. So right here, F stands for, let's zoom it in, F stands for freezing. So if we're talking about freezing or melting, then our K value is always going to be -1.86. Why is that? Because it lowers the freezing point. So that's why it's going to be negative, because you're going to decrease the temperature. All right, and then your constant for your boiling of water is going to be 0.52 degrees Celsius per mole. So why is that one positive? Because we increase the boiling point. All right, and then lastly, you have your M, which stands for molality. It's basically another way of measuring the ratio of how much solute is in your solvent. Example 1. What is the boiling point of a 0.62 molar solution? So there's our M of caffeine in water. So here's our molecule. We know that that is covalent. So that means my I, my number of particles, is just 1. All right, and it wants to know the boiling point. So that means I need to find the change in temperature so I can calculate that new boiling point. So as you see, I have the equation and all the variables copied over right here so you can reference them. We have a change in temperature equals our I, or our number of particles, times our constant for, what are we doing right here? We are boiling. So it is going to be the B times your molality. So let's go ahead and plug those things in. Delta T equals, my I is 1, times KB, which is always going to be 0.52. And then times my molality, which they gave me to be 0.62. All right, and when we multiply all of those together, we get a change in temperature of 0.32 0.3224. All right, so that is my change in temperature. It's asking me for the boiling point. Well, what is the original boiling point of water? We all know that the original boiling point is 100 degrees Celsius. All right, and so we know that what happens to the boiling point? Think about putting salt in a pot of boiling water. What does it do? It makes it hot. It makes the water have to get hotter in order to continue to boil. So boiling point elevation, that means that this right here is how much it increased. So 100 plus 0.3224. This answer is positive, so we are going to add it. So your new boiling point would be 100.3224 degrees Celsius. All right. Example 2. What is the melting point? So that means we are going to be using, what is melting the opposite of? Freezing. So I'm going to be using KF. That is my freezing and melting constant. Of a 0.17 molar solution, there's molal solution of potassium bromide, which is KBr. If we remember from Unit 3, I have a metal and a nonmetal. So what is this right here? This is a ionic solution. So I have two different parts. I have that K, which is the +1, the Br, that is -1. So I have two separate parts to this. So how many particles do I have? My I value is going to equal 2. Again, because there is two parts, two particles to that compound. All right, so keep reading. And potassium bromide. All right, so we've got our equation over here copied. Change in temperature equals that I value times the K, and we are freezing and melting right now, M. All right, so first we need to find our change in temperature to see how the melting point has adjusted. So change in temperature equals I, which is going to be 2. Here's where I got my 2 from. Then the KF, which is a negative 1.86. All right, it's negative because remember your freezing point drops. And then times your molality of 0.17. All right, and when you multiply all of those together, you get a change in temperature of negative 0.6324. So that is how much my temperature changes, but I want the actual melting point. So as we know, the original melting point of water, melting point / freezing point, is 0 degrees Celsius. All right, what happens when we add a solute to your solvent? It lowers the freezing point. Think about putting salt on the roads in the winter. It means that it has to get colder in order for the roads to freeze. That's why this answer is negative. So 0 minus 0.6324 gives me a new melting point of negative 0.6324 degrees Celsius. All right, so as you can see here, because this is dealing with our melting and freezing point, that constant is negative. If your answer is negative, then you will subtract it down here when you do your math. The one before this, our answer was positive, so we added it when we did our math. All right, because boiling point elevates, freezing point drops. All right, last example here. If an aqueous solution has a boiling point, so I'm looking for, I've got a KB value right here, of 112 degrees Celsius. This is a temperature. What is the effective molality? We're looking for M of the covalent solute. It's telling you that it is covalent, means it's one particle, one big particle put together in a molecule. So your I value is going to be 1. All right, when we look at our formula, change in temperature equals number of particles times your boiling point constant times the molality. If I'm looking for M, then I need to find my delta T, but all they gave me was T. Delta T means the change in temperature. So what is the original boiling point of water? 100 degrees Celsius. So delta T means I need to find the change or the difference between those. So 112 minus 100 is a change in temperature of 12 degrees Celsius. So that is my delta T. Now I can plug that into my equation with the rest of my variables. So I have 12 equals I, which we found to be 1, times your KB of 0.52 times the molality. That's what we're solving for. So I'm going to simplify right here. So I have 12 equals 0.52 molality is what I'm looking to solve for. Divide by 0.52 on both sides so that those cancel, and I'm solving for M. So I get a molality of 23.07. So as I mentioned, there are 4 colligative properties that determine how your solution is going to change as you add solute and increase the saturation of your solution. So that fourth one, the main thing you need to know about it is the osmotic pressure is going to increase. That is due to that difference in concentration. As you added that solute, you increased the concentration of your solute and created a stronger force of osmosis, which is the force at which that solvent is moving across the semipermeable barrier into that container. So osmotic pressure increases as you increase the amount of solute. Lastly, we're going to take a quick glance at this table, and all it does is just review over everything that we just talked about and all of your colligative properties that we've discussed today.